Alright, so image quality calculations. Alright, first question. A time of 1.5 minutes is required for a particular fluoroscopy exam whose exposure rate is 275 milliroentgens per hour. What's the approximate radiation exposure for the radiologic staff present in the fluoroscopy room during the exam? And we can't see the answers, they're obscured by this toolbar on the side, but just know that 183 is A, etc. Right? First thing we're going to do is honestly just divide 275 by what? How many minutes are in an hour?
60.
Yeah, so we're going to divide, I'm going to turn on this. So, yeah. And 275, which gives us what? 4.58? Okay, so that's 4.58. And the way I would proceed from here is maybe divide that by what? I could divide that by half, because I've got to, this gives me part of the answer. That gives me the 1 minute. But I also have another half minute, right? So if I divide 4.58 by 2, that's going to give me the half minute. So that gives me 2.29. So I'm just going to say 4.58 plus 2.29, and that's going to equal something close to 6, right? This 697. Right? Does that make sense? Did I skip too many steps? Okay. All right. All right. Next question. If the exposure rate to an individual standing 4 meters from a source of radiation is 10 milliroentgens per hour, what will the dose received after 20 minutes at a distance of 6 meters from the source? So what's going to happen, first of all, with the dose? If we increase our distance, we're going to decrease our dose, right? But it's also getting fancy because it's asking us an amount of time, like 20 minutes, right? How many 20-minute intervals are in an hour? 3. 3. There's 3 20-minute intervals in an hour, so that might be helpful to us as we're solving this problem. So the first thing we're going to do, though, is start putting this stuff into the inverse square law, right? So what we need to solve for is going to be a radiation exposure. So the first thing that we need to solve for is just what the milliroentgens per hour are at this other distance, right? And applying the inverse square law, we're going to put the 4 down on the bottom and the 6 up on top, right? Does that make sense so far? So this is going to give me 10 times 16, right? I'm skipping some steps here, but that gives me 160. Equals 36x. Did I skip too many steps? So if I divide 160 by 36, just a sec, 160 divided 6, 4.444. Now we notice this is a distractor, right? Because that's the answer to, that is x, right? 4.444 is x. But it didn't ask us what the milliroentgen exposure per hour is going to be. It asked us what it's going to be after 20 minutes, right? And we know that 20 minutes is a third of an hour. So we need to divide 4.444 by 3. And that gives us the correct answer. Does that make sense? So I just divided 4.444 by 3, and it gave me 1.81.8. It's just a repeating number, right?
Wouldn't it also be easier to just convert it to milliroentgens per minute, so you don't have to worry about that?
Yeah, you can work it that way as well. You could convert it to milliroentgens per minute.
I just feel like I would forget that.
That is another workaround. So to do that, how would we do that, Katie?
You would multiply 10 by 60,
Will we multiply it by 60?
because there's 60 minutes
Ye-
an hour.
Okay.
So it'd be 600 milliamps per minute. Right?
No, we would divide it by 60. Because we're getting 10 milliroentgens per hour. So every minute we're only getting point.
1 hour, 60 minutes. Those will cancel each other out.
But that is one way that we can go, is to divide 10 milliroentgens per hour by 60. Okay. Which of the following groups of exposure factors will produce the most radiographic density, right? What is this asking us to do? Just find the mass. Find the mass for all these things. So 100 MA by 50 milliseconds. I'll work each one of these out. So 100, and it's going to be times what? Point.
You're going way too fast.
Am I going too fast?
Yes, it's way too fast.
Okay.
I'm still trying to write down everything that you're saying.
Well,
So that it makes
these
sense later on to me.
slideshows are up. They will be available on YouTube. If I'm going too fast, I will slow
Well,
down.
can you just write down the formula you're using? Because that would help.
Yes, I will write down the
Just write
formula.
it down the formula first, then I know what I can follow you from there.
That makes sense. Yes, that's a good point. So the formula that we're going to use for this is what? MA times time, and it's going to be in seconds, right? We're going to put the time in seconds, and that's going to give us mass. So mass equals MA times time. I'm going to make a note. Give formula first.
Yeah, because then you can go as fast as you want as long as I got the formula.
Rock and roll. That makes sense. That's a good note. Okay. So, but it has to be time in seconds. And all of the times here are in milliseconds, right? Now, the nice thing is they're all in milliseconds, so I don't really even have to know how to convert to seconds, right? I don't necessarily have to convert these to seconds. But if I want to convert milliseconds to seconds, so 1 second is going to equal how many milliseconds? 1,000 milliseconds, right? So, to figure out the first one, it's going to be 100 times what?
0.05.
Yep. Okay. Does anyone want to shout out what the answer is to that? So 5. Okay. The next one down is going to be 200 by what?
0.04.
Correct. By 0.04, and that's going to give me 8. The next one is 400 times 0.07 equals... Let me double check, sorry.
I have 20.
So 400 times 0.07. 28. So we're going up. We're going up in our technique, right? And the last one is 600 times 0.03.
It's 18.
Yep, 18. So it's asking us which of these will produce the most radiographic density, and we've arrived at our answer with 28. So that was this one right here, 400 MA at 70 milliseconds. Now, the quick way to maybe go here would be to just look at, to try to figure out what's our maximum amount of time and what's our relative to a fairly high MA, right? So I know just looking at that, I'm just trying to figure out if it's just 400 or 600, right? So without doing all these other steps, I could probably just go ahead and jump to 400 versus 600, right? Because all of these millisecond measurements are pretty close to each other, right? Now if one of these was like 1,000 milliseconds, then I would need to kind of reconsider that. But in terms of trying to get through these problems quicker, look at the MA first and then start looking at the time. Okay? All right. A 5-inch object to be radiographed at a 44-inch SID lies 6 inches from the image receptor. What will be the image width? So it's asking us to figure out magnification. So if we look at our book, the chart, it kind of gives us some different ways to calculate magnification. Where's that on page 235? 236. So 236, it talks about magnification equaling SID over SOD, and that's going to give us our magnification factor. Another way we can think about this formula, rather than kind of the way that they've given us, is to say the image size over the object size equals SID over SOD, the source to object distance. Okay? So if I plug the numbers into that formula, I have an object, right, that is 5, and I want to know what its image size is going to be, right? Now, here's where things get a little tricky. I know what my SID is, right? My source to image distance is 44, but they're saying the object lies 6 inches from the image receptor. So I have to do what with my 44? Yep, subtract 6 inches. So 44 minus 6 equals 38, right? So this gives me 38x equals 5 times 44, right? 220. So if I divide 220 by 38, I get 5.7 something. So there's my answer. B is the answer. Any questions about that? That is a very helpful formula to have. The image size over object size equals SID over SOD. You might want to write that in your book near their information on magnification factor. Image size over object size equals SID over the source to object distance. Okay. Moving along. Okay. Using a 40-inch SID, how much OID must be introduced to magnify the object 2 times? Right? So there's a way that we could work this out algebraically if we wanted to, right? But we could also think about it geometrically, which is going to be one of the keys to kind of the shortcuts to these problems on the test, right? So let's draw it out real quick. Pretend this is my radiation source, and what am I drawing coming from the radiation source? It's divergence, right? And they're asking me about, so this is going to be my image receptor down here, right? And they're saying that I have a 48-inch SID, right? And it's asking me, as I change where my object lies in this field, how much am I going to have to change it to magnify the object 2 times, right? And the way magnification works basically is the closer that we get to it, the more magnified it's going to be, right? And if we want to magnify the object 2 times, we just need to go like half of it. So we would need something like with an OID of 24, right? So that is a geometric way of thinking about this problem. Would it be helpful to see kind of also the algebraic way of doing this problem? Okay. Let's grab our little formula in the book. So we have an object and we're just going to arbitrarily give the object a size, right? Just for the purposes of working this algebraically. And the the object size that we start out with is going to be 2, right? And we're going to put it, I'm sorry, I've got things backwards here. Let me erase this. Because it's the object size over the image size. And we want the image size to be what? If our object size is 2 and we want to magnify it 2 times, we want it to be 4. So I just used 2 just to keep it simple, right? And we're saying the image size over the object size equals SID, which in this case is 48, and they're asking us at what source to object distance. They're asking us what is the OID, but we're going to solve for source to object distance and then we'll be able to compute the OID. Does that make sense? So we're going to say, let me turn my calculator on. We're going to say 4x equals 2 times 48, 96, right? 96 divided by 4 equals 24, right? So that is our source to object distance now, right? To find what the OID is, so this is our SOD. But if we want to know what, and what we know about SID in this case is it equals SOD minus OID, or plus, I'm sorry, OID. So in this case where we have an SOD and we have an SID, we're going to subtract to get the OID. So OID is going to equal the SID minus the SOD, right? So in that case it is 48 minus 24, which equals 24. So the answer is D. So there's 2 different ways to think about this. We can think about it geometrically or we can think about it algebraically.
So you just want to, like, what if we just picked a random other number that wasn't 2? How would that work out?
I used 2 and 1 and it still worked.
Yeah, with any number that you plug in there. But this is just pick an easy number. Don't like pick pi, right?
Well, I did 2 image and 1 object because then I was able to do it all in 10.
Yeah. We're just going to need, I picked the number 2 because it's easy to multiply 2 times 2. That's a good question though. Okay. Any other questions on this one? Because once I go forward, I can't go back. We're more than halfway done. So, for this one, it's asking us about grids, right? So again, if we look at page 236, it's going to tell us a little bit about grids, but we talked about grids earlier. So we're starting to memorize what our grid factors are. A particular radiograph was produced using 12 mass and 85 kVp with a 16 grid ratio. So what's the grid factor for 16? 6. The radiograph was to be repeated using an 8:1 grid ratio, which has a grid factor of 4, I think, right? What should be the new mass, right? So if we're decreasing the grid factor, what can we do to the mass? We're going to decrease it. Knowing that doesn't give us any hints, but the answers kind of help us know that we're talking about decreasing the mass, right? So we're going to start with, there's a number of ways that we could work this, right? But initially we had 12, right? And I think that I think possibly the easiest way for us to do this is if we want to know what the mass is, right? They have a formula here. Mass 1 equals grid factor 1 over, we don't know what mass 2 equals grid factor 2, right? So we can cross multiply then. So we're going to say 12 times 4 equals 48 equals 6x, right? 48 divided by 6 is going to give us 8. So we were able to decrease our mass to 8 mass. That formula is there on the page. If we decrease our grid ratio, we can decrease our mass. And it's just according to this formula, mass 1 over mass 2 equals grid factor 1 over grid factor 2. Okay? Questions about that? There will be a question about that or two on the quiz. Okay. Moving along. So we're on question 7. We've kind of upped the ante a little bit. Of the following groups of technical factors, which will produce the least radiographic brightness? The least radiographic brightness, right? So if it's the least radiographic brightness, it's the most radiographic density, right? So this is an old problem. They've just put new wording on. So we know the least radiographic brightness equals an increase in the density. Okay? Just different ways to think about the same stuff. So going back to, so again, we can think about this geometrically or we can think about it algebraically. But what are going to be the controlling factors of the techniques that we have listed here? What are going to be the controlling factors to density? Mass and SID, right? All of the KVPs are fairly close to each other, right? They are, one of the things that's important though is that they are 15% different, right? So of these techniques, the highest one in terms of, there's actually two here that are more or less equivalent, right? Answers B and C are pretty much the same technique if we're not looking at SID. If we're just looking at mass and KVP, right? They're the hottest techniques. But they're also more or less equivalent, right? So the only thing that's different between those two techniques is what? The SID. This one has a much smaller SID, They are. They shouldn't be. They were supposed to
Should
be.
the last one be 36 SID?
No, it was something else. I think it was 44. Imagine this was 44. I'm sorry, y'all. You get 25 cents. I wrote all these problems myself, which is a lot of fun, writing word problems at 2 o'clock in the morning. But yeah, so that's my excuse. So if that were the case, that would make these two equivalent then, right? It would make these two guys equivalent because they have an equivalent SID, and then the mass is compensated for by a 15% difference in kVp. So the one with the smallest SID is the one that sticks out. Okay, so the correct answer is B. So I've applied several rules though, right, in arriving at that. I applied the 15% rule pretty quickly. And this is why I'm stressing this stuff so much, is we need to be able to apply it on the fly to a question like this. And then the other rule that I applied really quickly was the inverse square law. I didn't work it all the way out, but I had a good foundation in it, a firm enough foundation in it that I knew that this increase in SID was going to bump things over the edge, right? And it was going to create the most density, the least radiographic brightness. Questions about that? So without doing all the math, I applied both the 15% rule and the inverse square law to arrive at that answer. Okay. All right. We're coming down to the end. A satisfactory radiograph of the abdomen was made at a 38-inch SID using 400 mA, a 60 millisecond exposure, and 80 kVp. If the distance is changed to 42, if it's increased, what new exposure time would be required? So it's saying we're going to keep our kVp the same and our MA the same. What new exposure time would be required, right? So this goes back to the square law, right? Not the inverse square law, but the square law, which says that mass 1 over mass 2 equals what? SID 1 squared over SID 2 squared. Right? Now, one little cheat that I can use here is I don't really need to compute mass, right? Because it's told me the MA is going to stay the same. So I can kind of skip computing mass and just think about the milliseconds, right? So I can, rather than computing mass, I'm just going to make a workaround and I'm just going to say 60 milliseconds, right? Over X equals, the initial SID is 38 squared over 42 squared. Is everyone clear on why I skipped that step? Because I would just be making extra work for myself. So 42 squared is some huge number. It's like 117. Over X. And then 38 squared. 1444. This is why they allow us to use calculators on this test. So I'm going to move back up here and I'm going to say 105,8400 equals 1444x, right? So if I just divide that by 1444, I get 73.2. So x equals 73.29 something, and I'll round up to 73 milliseconds.
It's a lot easier. I worked it out the hard way.
You worked it out the hard way. And so the hard way would be to calculate the mass, then apply the formula, and then subtract, and then divide out 400 MA, right? Yeah, that's the hard way. But if I know the MA is going to stay stable, all I'm really solving for is the time. There's a good learning point there. So we're on the very last problem. Any other questions about that one? Okay, let's go to the very last one and we'll be... All right. This is asking us to think about all this stuff now, right? And it's saying we have an initial technique and a new technique. So we've changed our KVP, we've removed the grid, and we've changed the SID. We've got to think about all of those factors now, right? So the first thing I'm going to do is I'm going to figure out exactly how much the KVP has decreased, right? So, and the way to do that, very first thing I can do is I could figure out what is, so it's more than 15%, right? I'm just plugging in numbers now, in all honesty. It's about 30% decrease, right? So it's about 30% decrease. So decreased about 30%. So I know already if I'm making that kind of decrease to the KVP, I'm going to have to make compensations to change my density, right? One of the compensations it looks like this tech did was they removed the grid. So we had an initial grid factor of what? Like 5, and now we have a grid factor of 1, right? And then they also decreased the SID, right? They changed the SID by 16 inches, right? So they decreased the SID by 16 inches. Okay. So, and yeah, the initial mass we already know was 100, right? So we're going to look at each one of these factors and just start calculating one by one what these factors would do to our mass, right? So if we decrease, if we want the same technique basically, but we've decreased our KVP, what do we want to do to our mass? Yeah, in this case we're going to quadruple it. So let's go ahead and just say the mass has gone up to 400, right? So there we've accounted for one of our changes, right? Now let's account for the next change. We changed the grid, right? And what we know about changing the grid is that initial mass, so let's say the initial mass, so this was kind of 1. We're going to kind of compute all this stuff together. So we said it was 4 times. The initial mass was 100, and that was in the 5. The new grid factor is 1x, so it's 5x equals 100, right? So x equals what? 20. Yep. So this is saying the change in KVP is going to increase the mass. This is saying the change in the grid needs to decrease the mass, right? And that would be by a fifth. Okay. And then the final thing is the SSD. So we're going to go ahead and apply the inverse square law. And we're going to say 100 over x equals, oh, actually, we'll just apply the square law in this case. So 40 squared, or I'm sorry, 56 squared. Bear with me, I'm sorry. (56) squared over 40. So 51. So we nearly halved it, right? So here's what we'll do. We're going to just go piece by piece with that. So we're going to say 400, and then we're going to say 400 divided by 5 equals 80. So that's, do y'all understand how I'm doing these steps? I said 100 times that gives me 400. 400 times that gives me 80, right? And then 80 by that gives me 40. So the new technique should be close to 40. I guarantee you there's going to be at least one board question about this, and I want you all to get it. But understand that it requires us to know each one of these steps. So we needed to know the 15% rule. We needed to know how to do a grid factor conversion, and we also needed to know inverse square, or the square law.
Can you give us some of those to practice or something? Can you give us some of those to practice?
Yeah. Yeah, definitely.
Like, I understand it, but if there's so many steps, it's like...
There's a lot of steps, and there's shortcuts, but I want us to get these foundational steps first, okay? So that's it for today. Let me turn this thing off. Okay, there was a little bit of confusion about how the problem has worked, so I'm going to walk through kind of the narrative way that the book introduces the problem, and then I'm also going to talk about kind of what I'm trying to get at, which is kind of pattern recognition kind of stuff. So the first thing the book wants us to do is to figure out how the technique is going to change if we go step by step, right? So the very first thing that we've changed is we've decreased the KVP. So we need to figure out what percentage we've decreased the KVP. And so Chris has a really nice, neat way of calculating the actual percentage, which is to subtract whatever the higher number is from the lower number. To subtract, appropriately so that you have just the mean difference, the difference between the two numbers, which in this case is 22, and then you divide that by the initial one. So in this case we have 0.275, which also gives us about 28%, right? Okay, so that's very close to 30. So we know right off the bat that our mass is going to have to quadruple, right? Because this is twice 15%, right? So the very first thing we'll do is we're just going to multiply our mass by 4. 400 mass. Now let's look at the next step, which is we're going from having a grid to not having a grid, right? So we're going to take this number, 400, and we're going to plug that into our grid factor conversion formula. So it's going to be 400 over x equals, in this case, 5 over 1. So now x equals 80. Okay, so that dropped our mass down because we removed the grid. Okay, now we're going to plug that into the square law, right? Because we have to account for this change here, right? So we're going to say 80 over x equals 56 squared, which was that initial one, over 40 squared, right? And if we work that all out, it's going to come to 3136x equals 12800. And the final answer is going to be x equals 40.82 mass, right? So that would be our final answer, that we're going to have a decrease of mass. So now that we have that understanding of the problem, I want to kind of reiterate one of the things that the board is asking us to do, and one of the cheats that we can find, right? So the very first thing that we can identify is that this is a decrease in KVP, and whenever the board, on a problem like this, if it's decreasing the KVP, it's either going to be by 15% or 30%. So I can just look at this and tell that it's 30%, right? Anytime we're going from a grid to not having a grid, if we're going from having a grid to not having a grid, we're going to be dividing, right? If we're trying to find the mass, we're going to be dividing. So it's just going to be 1/5, right? Because that's the grid factor just expressed as a fraction. And there's nice numbers that you can look for when you're talking about the square law. In this case, it's this is a nice number because it's 16, right? And what we know about this number is that it's always going to equal half, right? So if it's decreasing the SID, I'm going to need to half it if this number is 16. If I'm increasing the SID, I'm going to need to double it, right? But this is just another way of thinking about this stuff, that rather than working all the formulas, we can just try to identify these patterns based on the 15% rule, based on understanding grid factors, and then also based on the patterns that the board applies to the square law. Hopefully this is helpful. Thank y'all.